Nice to be here, and I'm Han, coming from Phala Cloud, and today my topic is about building private first AI with trusted execution environment. So the first two talks in this series has been focusing on different angle of confidential computing. So I'm going to dig into the technical detail and how we implement such confidential AI using confidential computing technologies. So it's going to be a little bit technical, but I will try to make it as simple as possible. So a little bit about myself. We have been creating this company for roughly 8 years. So starting from 2019, we created our company called Hash Forest. That's the company backing Phala Cloud. And now we're offering just a native cloud to simplify everyone's work to deploy something into TDX. And specifically in this talk, I want to talk about the use of confidential computing in AI. So when dealing with AI workload, there is a big problem that's never more serious before. So that is the trust problem. If I take an analogy to a typical secure system, then usually we measure the system in three different angles. So first is correctness. If there's a system running something, you want to make sure it's exactly compliant with the behavior you expect it to behave. And the second one is privacy. You want to make sure if you talk with, for example, some AI model, nobody else can see your inputs or outputs. And also liveness. If some system guarantee tell you you can always interact with this system, you shouldn't be locked outside of this system without a good reason. But here, I think the most immediate demand in the ecosystem is focusing on privacy. So we want to make sure if we're talking with an AI model, nobody else can see the inputs or outputs, even not the model provider, even not the cloud providers. So let me just go that pretty quick. And in an ideal world, like this is a diagram showing a typical stack of AI inference. In the ideal world, on the left side, we have the user, and the user already has the end-to-end encryption between the user and the server. So this can be encrypted by like a TLS protocols. But on the other side, the model running on the server is out of user's control. And it's controlled by the model providers like OpenAI, or controlled by the cloud provider like Azure. So technically, both OpenAI and Azure can tap into this server to see what's running. They can dump the memory, and they can see they can intercept the inputs and outputs to see what's happening there. Those are already the plain text in the memory. So technically, if they want, anyone can do that. And in an ideal world, what we want it to look like, what if we can log everything running in this server in a black box? So by a black box, I mean it can run the AI inference workload inside this environment, but at the same time, not the cloud provider, not the model provider can see anything running inside. And in this ideal world, the user and the inference server is end-to-end encrypted without anyone being able to intercept anything or pick or manipulate how the program is running in this environment. At the same time, the user can be convinced that this is really the truth by having a proof from this system. And this magic black box, is really ideal, but it turns out it exists. So that is a trusted execution environment, and I'm going to introduce that later. But when we talk about privacy, maybe 99% of the people in the world, they are going to come up with another option that is on-premise deployment. So of course, you can buy your own hardware, put that in your own database or your own office, and then you use that, cutting the network access. So you're all good. Nobody can see what's happening there. But there are still a few problems. So first is you're going to pay all the hardware cost. That's pretty high if it's a smaller team. And at the same time, the utilization is really low because based on our experience, usually if you deploy like a H200 DGX within your team, the utilization is around maybe 10% to 30%. So in at least 70% of the time, the hardware is idle. So you're wasting your money. And more importantly, What if now you're not just using the model by yourself? Now you want to offer your service running those models to someone that don't want to trust you. So in this case, the trust boundary in on-premise deployment is only between you and the model, not your user. So you can't really convince your customer what's happening in this trust boundary. So to solve those problems, we want something more powerful. So that is a trusted execution environment. So as a few other speakers has already introduced, so trusted execution environment is a special mode in your hardware. It's not very special. So like your Intel CPU, AMD CPU, and NVIDIA GPUs, they may already have the capability to enable the trusted execution environment. And once it's enabled, it isolates everything in a very strongly enhanced environment where nobody can see what's running inside, and it can prove what's running inside without revealing the memory, the inputs, outputs, the data, and the intermediate states. So with this very powerful primitive, we can actually build the entire secure and private AI infrastructure on top of that. And this is how that looks like. Basically, we put the inference stack running in a trusted execution environment. And we can prove to the user this is really running in an environment so that nobody can manipulate what's running inside. And it turns out the performance overhead is pretty small. Usually it's between 1% to 5%, depends on what kind of the workload you're running. And another benefit is that with this trusted execution environment, you don't have to put all your workloads in your own office or your own data center. You can now outsource arbitrary computation to a cloud to make your inference stack more cost efficient. And you can even convince your users by showing them the proofs. Okay, so with this in mind, how can we build a real confidential AI serving system on top of TEs? So on the hardware side, actually, there's a long story. Trusted execution environment is not a very new technology. The first version of TE is probably launched in 2015. That was Intel SGX. But as you can see, the capability is not that strong. For example, you can only run very tiny code within 64 megabytes of the memory. But later on in 2017, we have next generation of the TE. So now you have the full virtual machine, and you can put arbitrary workload running in the virtual machine there. So now you have the operating system, you have Linux, you can basically run whatever you want, including containers. And then Intel TDX, and then in 2022, we can even run a GPU workload. So now it's not just a small CPU workload, you can run very large LLM. And in Hopper, it's just one GPU. Blackwell, you can have 8 GPUs. And in the next generation, you can even have 144 GPUs interconnected together to run really large model serving and maybe even some fine-tuning. That is the hardware. And how about the software? As a benchmark, we know a team that is our partner. They used to run some software in the very old day TEs. It took them 6 months to port such software into TE just because it doesn't run unmodified code. And then in 2024, with Intel TDX, they can just port their code into TE within a few weeks because now they don't have to change their code. So greatly reduce the burden on the developer side. And then later on, we have some open source frameworks and some clouds that enable you to even just run unmodified container within one click. So greatly simplify the developer experience. And with that, to build a private inference system using CPU and GPU TE, a very, very minimal inference stack is that we should have an inference engine running in the TE. And now the most popular ones are VLLM and SGLab. And second one is once we run this in the TE, we want to let user to know it's really running in the TE. So we have to expose the remote attestation from TE. So remote attestation is basically the proof generated by the hardware. So the user receives the proof, they can verify the proof to be convinced this is really the expected workload running in the TEE. So in this case, some open source models. And let me show you a very concrete example of how deploying workload in TEE looks like. So we have like an open source project called dstack. It's also part of Confidential Computing Consortium. And what it does is it can enable you to easily deploy any container in just a few minutes. So this is fully open source, and if you want to check it out, you can check it out later on. And we also have like if we follow this tutorial, confidential AI, then you can see basically deploying that in a TEE is as simple as you define a container, and just in the same way as you deploy the container outside of the TEE. And then once you have the container deployed in the TEE, in this case, confidential VM, and you can have another component to expose the attestation and serve that to the user. So on our cloud, as you can see, you can simply deploy something very easily like this. So in this case, it's a VLLM. Oh, there is a SGLang running the GLM 4.7 flash model. And this is the full config and fully running on production. And once we have this, the next thing is how do people convince this is really a model running in the TEE? So this is how this is what the remote attestation solves. So how does a remote attestation look like? So here, this is a user interface of private chat. So if you check, then here you can see I can choose some models running in the TEE, and I can click TEE verified. So on the right side, it can show you the remote attestation. So this is the proof. One proof coming from Intel, so this is running on an Intel CPU, and one proof from NVIDIA to show this is a really NVIDIA TE GPU. So you can get all the evidences and verify that by yourself. And then, but although now we show you how you can deploy everything and verify the proofs, but how does the proof mean? Why can you be convinced this is end-to-end private? So it turns out you want to verify the things on at different layers. So first is application. Of course, you want to make sure there's no backdoor. Even if we put a LLM in a TEE, and you can still maybe inject some backdoor to log the user request, right? So we don't want that to happen. So we can prove that by showing user the provenance of source code. So here is the GitHub commit. Here is the program. You can check the GitHub commit to make sure no backdoor in the code. Second one is you want to make sure the communication is end-to-end encrypted, so nobody can see the communication. And not only that, but also the operating system, because the application security and communication security is also guaranteed by the operating system. If there's a backdoor on the OS side, you also get compromised. And of course, finally, the platform, CPU and the GPU TE environment. So combine all these things together, we get something called the full chain of trust. And this is it really takes some time to secure every layer. And once we got that, you can verify the proof. And this is just a screenshot of one of the TDX proof verification service. You can just copy and paste the proof and verify that by yourself. And this is a screenshot of a real proof, the decoded TDX proof. So basically you can see all the fields are just some numbers. If you don't know what it means, it's really hard to convince user why the application is secure. So that's why we have to build the entire ecosystem to explain what are all those measurements, how the reference value can be produced, and how can link that to the source code and all the supportive materials. And this is another example of how we can link all the evidence together, so it can make the auditor easier to verify all the components are linked together. But there's also another challenge. So far, we have covered how can we run a single LLM in TEE, but in the reality, there are many platforms. Like we have NVIDIA confidential computing, but at the same time, we have Intel TDX, AMD SEV, and SMP. They all have different format of attestation and different ways to verify the attestation. And on top of that, we also have a lot of different implementations. Like for us, we run the Phala Cloud and we run a few models, and we have our own format. to expose the proofs and evidences. But there are also other providers like Tinfoil, Near AI, Private Mode AI, by Ageless Systems. So everyone has their own version of the attestation and their own API. So it ends up be a burden on the verifier and the users. So you have to understand all the formats. So on the non-TE world, people tend to use an aggregator. So like OpenRouter is a router for a lot of model providers. And on the TE side, we also want to bring this as simple as using OpenRouter. So that's why we have created RedPill. So RedPill is an aggregator, so you can have a lot of models. Those models are all TE models, and we produce a unified API for users to use. So if you check now, you can see we have almost all the latest models available there. And probably it also makes sense to have some standard so that every model private inference providers can share the same standard, and verifiers can easily understand them and verify their outputs. And yeah, so far we have covered a few things, right? One is what is TE and how we can use TE to secure private inference. And we have also covered in the ecosystem with a lot of different fragmented implementation, how can we standardize them? But there are still a lot of future challenges I want to point out. So one, standardization. We have covered attestation and platform. So ideally, there should be someone or some standard so that the model developers or model providers and the users don't have to deal with all the platform differences. And second one is performance and scaling. Although running a single workload in the GPU only have 5% of the overhead, when in production serving, we want to make sure we have very high throughput, and that is good throughput. The latency, the latency of the first token, the latency between the tokens should be compliant with some SLA. So with that, PD disaggregation, which is some tricks to serve the model on production, should be implemented. But this is still a challenge because now we don't have a way to interconnect many GPUs together. Maybe Vera Rubin can eventually solve this problem. And ecosystem and composability, there are a lot of systems already running in the non-TE system, and they want to talk with the TE system in a way that is not invasive. Like how can a system to relay the user request to TE without seeing the inputs and outputs? So this may introduce some other challenges like end-to-end encryption at the application level. And finally, sandboxing. So you can imagine OpenAI, Anthropic, they are not going to open source their model weights. So they have their proprietary LLM inference stack and also proprietary LLM weights. So we want to make sure they can also run that in the TE without showing just open source everything. So Sandbox aims to solve that problem. So the good news is that the entire ecosystem is working on all those challenges, and they already have a lot of promising progress. All right, so overall, we have talked about how we can use TE to secure AI inference, and probably not only AI inference, but also AI agents. Now, the overhead is not super high, 5%, but of course, if we want to achieve production level inference service level, we want to make it even better using PD disaggregation. And the ecosystem is pretty good. We have really good hardware, and the software is also way better than before. And combine them together, we almost solve the trust problem in AI. So that's like what confidential AI aims to solve. And like next frontier, there are a lot of challenges and a lot of people making good progress solving those challenges. So yeah, that's a wrap. And thank you for listening to this presentation. And dstack, if you haven't checked dstack out, please check it out and start that. so that you won't forget it. This is purely open source, and you can use that to instantly turn any T-enabled hardware into some stack ready to deploy your confidential AI workload. All right. Thank you, everyone.